This is the fourth lecture in this series of lectures in special theory of relativity. So last week, we actually, after introducing the idea of special theory of relativity and why it was required, we figured out that there is a whole bunch of different transformation laws which are to be there in order to satisfy the postulates of special theory of relativity. The key point was the constancy of the velocity of light. So when it involves light, things are really different. It has to, the new ideas have to flow in, which are kind of counterintuitive from the point of view of pure mechanical waves. And we found out that the Lorenz transformation is the appropriate one, which takes into account things like loss of simultaneity that we had first discussed before introducing the Lorenz transformation. This loss of simultaneity in frames, as you change the inertial frame, is well taken care of through these transformations. And then we found out that there are important, very important, and sort of conceptually challenging uh, stuff, like even the length, the measurement of length, the length and the time, both of them are a kind of non-invariant depending upon the frame. So with respect to an observer who is thinking himself as stationary and the other frame is moving, so according to him, in the moving frame, the length is contracted and the time is dilated. Okay, time runs slow over there. So this point, actually, I would like to say one thing: what is meant by time runs slow? Because people may get sort of easily confused with that. That is the very statement that moving clocks run slow. What does that mean? What it means is that a clock moving at a constant velocity with respect to an inertial frame that contains synchronized clocks will be found to run slow when timed by those clocks, right? So basically, to time a clock moving at constant velocity relative to an inertial frame, we need at least two synchronized clocks in that frame. So with respect to these two frames, the situation is equivalent. With respect to one, it depends on where you are, which frame you are referring to. So in each one's frame, the time in other frames will be running slow. So that means if you want to estimate the age of something, then in each other's frame, it will look like the person who is measuring in his rest frame, he has aged more than the other person who is in a frame which is moving with a constant velocity with respect to the previous frame. The words may sometimes, look a little baffling, but let me try to illustrate or may make myself much clearer. Suppose you have when do we say a clock is moving slow in our usual perception? What does that mean? It means that suppose I want to, once again, coming back to the reference of estimating the age. Suppose today is my birthday. Okay, I was born, say, 50 years back at 12 p.m. on this day. So at 12 p.m. today, I would be completing exactly 50 years. And I put a clock in my drawing room and I say that, okay, or I put two clocks, okay, at the same location. I synchronize them. I'm happy with them. And I would say that from 12 o'clock in that clock, both the clocks, I start counting time, and I will once again come back to them when there is 1 o'clock at those clocks. And then I will say that, okay, right now I am 50 years, 1 hour old. Now, the hands of the clocks are moving, and I come back thinking that it's 1 p.m. And I found that, yes, in one of the clocks, the short hand is at 1 in the dial, and the long hand is at 12. So it's 1 p.m. When I look at the other clock, I find out that, yes, the short hand is close to 1, but the long hand is at 9 or at 10. And I infer that, okay, the other clock is running slow. It's 10 minutes slow. When I make that statement, what do I mean by it? How do I measure, let's say, or give a statement on, okay, 5 minutes have elapsed. How do we do that? That when, suppose both the hands of the clocks are at exact 12, and then when the uh, larger hand has moved to the next dial, I mean, next number, big number in the dial, I estimate that time to be 5 minutes. I call that this is the 5 minutes. Okay, now what is happening to this other clock, which I called slow, is that we are calling it slow? Because in getting to cross from this dial number 12 to the dial number 1, it is taking more time than the other one. Okay. For it, the concept of 5 minutes is taking a longer duration. So then we say that, okay, this clock is slow. So therefore, when we are using those clocks to measure my age, then I can infer that in the second clock, I am younger. According to the second clock, if there is an observer inside the clock, then he would infer that my age is 50 years, 45 minutes, or 50 minutes, while the first clock will infer my age is 50 years, 1 hour. Okay, is that clear? This concept of measurement of time, the concept of fast, slow.
Sir?
Yes.
Sir, but there could be a lot of reasons as to why the second clock is falling short by, say, 5 or 10 minutes, right?
Such as?
The clock which is falling short by, say, 5 or 10 minutes, there could be a lot of reasons for that to happen, right?
Such as?
I don't know, sir. I mean, in
Huh?
this scenario which we took, there is no frame such as, I mean, which is moving or something, right? So, how do we?
I once again I said, I mean, forget a moment that this is a special theory of relativity class. I am only trying to drive home the point of what is meant by a clock being slow. Okay.
Yes, sir. Then some sort of faulty appliance in the clock might make it slow.
Yes,
It could be
that's
a
that's, that's absolutely correct. I am not looking for reasons. All I am saying is the observer observes and reports.
yes, sir.
Okay. So when the observer says that according to my clock, you are 50 minutes, 50 years, 45 minutes old, all right? And the other clock says 50 years, 1 hour old. That means according to this second clock, okay, which is, in perfect synchronization with, numerous other clocks which we trust, that it's giving the right time, then that means according to that clock, I am older, isn't it? That is one way of looking at things.
Yes, sir. Yes, sir.
Right. So why I'm saying this, because at the end I will give you an example where you will understand that why I brought up that point, and that is within the realm of special theory of relativity. Okay. So all right. So first things first, as I was discussing from where this idea of, from where I started out this sort of trying to convince you about the concept of clocks running slow, is that special theory of relativity, once we introduce the Lorenz transformations, a formal way of writing the tenets of special theory of relativity, we found that time in moving reference frames are dilated. Time is slow. Things are moving slowly there, whereas lengths are contracted. Okay, these are the two mind-blowing uh, consequences of special theory of relativity, or the formal structure of it. Okay. So coming back to this concept of simultaneity, let us, because this I know might have been bugging many of you. So the question is that why is the fact that simultaneity is not an absolute concept is an unexpected result, because our usual perception tells us that the things that we see, observe, or experience, if something is simultaneous in a moving object, it is simultaneous in a quote unquote rest object as well. Okay, but the point is that the simultaneity is not an absolute concept, is all because the speed of light, and the speed of light has such a large value compared to ordinary speeds that we fail to perceive this concept of simultaneity is not being absolute, that simultaneity varies from frame to frame. So I'm going to illustrate with one example, which is our daily kind of experience, which falls under the category of our usual experiences. And I'm going to consider two cases which are symmetrical in terms of interchange of space and time coordinates. So in the first case, that's on your screen, a man on a train moving with 20 kilometers per second lights two cigarettes, one 10 minutes after the other. So according to the passenger, the events occur at the same place. We are all good with that. But according to the ground observer, the events have occurred at different places. He punches in the numbers into the Lorenz transformation. So you can see the V by C is a very small number. Okay, it's 10 to the power minus 8 orders. So it has hardly any effect on this. And so, therefore, we can, get this number delta x, that is these two events are occurring at a distance of 12 kilometers. All right, so that's very easy to see. I'm sorry, this is 20 meter per second, excuse me. This will be 20 meter per second. 20 kilometer per second is lightning speed. I'm sorry. So it's 20 meter per second, and you can see that if you didn't use the Lorenz transformation, you simply can calculate and say that yes, this is the result. All right, because 10 minutes means as many seconds, and then therefore it will be 12 kilometers. So this result is very consistent with what we can usually perceive. Okay, but then if I simply change the time and the space coordinates for the same problem, just interchange. So that is the case too, that the observer on the moving train is seated right at the center of the car and observes two men, one at each end of the car, light cigarettes simultaneously. In his frame, it's simultaneous. So passengers will say that events are simultaneous. In the first case, the cigarette was lit, the two cigarettes were lit at the same position in the train, that is in the passenger's frame. Here, the two cigarettes are lit at two different positions in the passenger's frame, but at the same time, simultaneous. Now, ground observer will conclude, if he is using the relativistic formulation, that man in the back of the car lit his cigarette before the man of the front, and the time difference between these two is, however, extremely small. It's 10 to the power minus 15 second, as you can see, which is hardly anything, which is like immeasurable, but theoretically there is a time lag between these two. So now result, even if it is small, it's 10 to the power minus 15, is kind of difficult to perceive for us, because we will still be thinking that these events are simultaneous. I mean, a ground observer will still think the events are simultaneous. And well, I mean, you cannot completely disregard them because this time is so small. Now, why is this happening? This time is so small is because of the velocities with which this train is moving. The velocity is no way comparable to that of light. As you can see, it's 10 to the power minus 8 orders of magnitude. Now, in case of time, it gets even smaller because we have in the Lorenz transformation, instead of V by C, we have V by C square. So that gives rise to this very small term, very small number. And as a result, although the case one that we just discussed, it puts us within the bounds of familiar experience, but it puts case two out of this bound. Okay. All right. So this simple example illustrates that why the concept of simultaneity is really challenging for us, for the objects with which we deal with in day-to-day experiences. But does that mean this entire special theory of relativity, I mean, as a formal theory, it's elegant, it's wonderful, but then it doesn't have any applications in reality, isn't it? I mean, looks like. Hang on. But there is a world in which it has tremendous applications. And this is in the case of the world of microparticles, where they are moving with very high speed inside a collider, and they are colliding, they are disintegrating themselves, giving birth to new particles and all that. There, the situation is completely different. Or in case of intergalactic bodies, okay, the things over there. So let me show you another example from the high energy physics. The case of charged pions. Pions have a mass between that of electron and proton. In fact, here you can see the charged pions have mass which is 273 times heavier than that of electron. Okay. And it can have positive or negative charge. So here we are considering positive pions. Now, these pions, they can be produced by bombarding a target in an accelerator with high energy protons. And then the pions actually leave with very high speed, close to that of light. It is seen that these pions are radioactive. And as like other radioactive elements, they have a shelf life. And when we consider the radioactive substances, the quantity that is appropriate is the half-life. People measure their half-life. So it is found in the experiment that the pions half-life, when they are brought to rest, is 1.77 into 10 to the power minus 8 second. Okay. All right. Now, that means that half the number of pions present in the pion beam at any time has decayed after this amount of time, as measured when they have come to a halt. Now, if we send a collimated pion beam leaving the accelerator target at a speed of 0.99 of the velocity of light, almost equal to the velocity of light, it is found to drop to half its original intensity at a distance of 39 meters from the target. So from the target, a pion's beam with very high velocity comes out, and then it is measured that after a distance of 39 meters, its intensity falls to half, which means half of the pions are exhausted. Okay. So we can have a good estimate of the half-life. Now, well, the thing is that question is the result consistent? Is the measurement consistent? Because this half a distance of 39 meters is a measured thing in the laboratory. Okay. First thing that could be baffling is that, okay, they are going out with 0.99 C and their half-life is 1.77 into 10 to the power minus 8. So if we multiply these two, the intensity will fall to half. That means half of the pions will vanish at a distance of 5.3 meters. A very simple calculation one can do. But hang on, the experiment says it's 39 meters. So what is going wrong? Here comes the time dilation that accounts for this inconsistency in theoretical calculation and in the experimental result. Now you see this tau naught that we are talking about. when it is measured when the pion is at rest. That means this half-life that we are talking about, it's a time, this time is the proper time in pion's frame. You remember in the previous class we had discussed about the proper time and the proper length. Okay, it is basically the measurements of time and length in a frame in which the system is at rest. So the observer who is sitting in that frame and finds the system at rest will measure the proper time and the proper length. In all other frames, it's improper time, improper length. Now, the mistake that we did over here was we are taking the proper time and simply multiplying it with the velocity and claiming that this is what it should be from, according to the measurements in the laboratory. See, laboratory frame and pion frame are different. This time is in the rest frame of pion, not in the rest frame of laboratory. So you are actually mixing things. Okay, you are taking the pion's rest time, proper time, and simply multiplying with the velocity, just the way Newtonian mechanics does, and then you are claiming that this is what should be observed in the laboratory. But that's wrong. What is happening is that in the laboratory frame, because laboratory frame with respect to pion is moving, the time as measured in the laboratory frame should be dilated by this factor gamma. I guess I do not have to remind you what gamma is. It's 1 over square root of 1 minus v square by c square. So with respect to the pion's rest frame, the laboratory frame is moving with a velocity 0.99 c. Therefore, a measurement of time in the laboratory frame is actually dilated. So you can see that this was 10 to the power minus 8 and it was 10 to the power minus 7. Now if you take this time and multiply it with v, you get back this correct distance that was measured in the laboratory, 39 meter. Okay. So this inconsistency can be removed only by consideration of the time dilation factor, which is a consequence of the Lorenz transformation equations. Had we not taken this into account, this time dilation factor, we would still be hovering over this number, and then there would have been bitter fight between an experimentalist and a theorist that your numbers do not match. So who has made the error? So in the first example that I showed about the trains, it beats our perception, and we can simply discard saying the case 2, the time is so small that it doesn't count. But in this example, you see a different thing, that if we completely want to disregard the ideas of special theory of relativity, and this time is not really that important, the time duration of something, we would end up on the wrong side of the truth. Okay. So in fact, this thing can also be shown from the length contraction argument. So that's what I'm going to show you now. Yeah. So from the length contraction argument, if you see the proper time, that is the time measured in the pion's rest frame, was this. In the laboratory frame, the distance was 39 meter. So now in the laboratory frame, from the laboratory frame, if we consider the pion frame is moving with a velocity v 0.99 c, then in the pion frame, the length should be contracted by this factor. And then you take that length and divide by the velocity, you get back this number. So you cross verify from time dilation and length contraction measurement that this is what is happening. Okay. So therefore, the point that I want to make is that in special theory of relativity, you have to be crystal clear about which frame you are going to use when you are dealing with particles or entities that are relativistic. The ones which are not relativistic, like the example on the train, you can still sort of get away with it, but not over here, cases like this. And this is not an isolated example, by the way. All the dynamical measurements in high energy physics are consistent with this time dilation and length contraction result. Okay. So these experiments and the accelerators themselves are designed to take into account these relativistic effects. So in high energy physics, for example, this relativity is a routine part of everyday world. Another is, of course, the cosmology, the study of stars, astrophysics. Okay. All right. Is this clear? Any question on this? If not, then I will move. Okay, very good. So it seems that people have understood it, discovered the importance of this thing, and that at least, places where these relativistic ideas are routinely used, and if they are implemented in a wrong way, you end up getting discrepancies like this: 5.3 versus 39. All right. Now, one thing we left out in the previous lecture, when we are talking about transformations, is that how the velocities transform. We have seen in the case of Galilean relativity, the transformation of velocities from frame to frame is straightforward addition of velocities, nothing else. But over here, in the Lorenz transformation case, in the realm of special theory of relativity, things are slightly different. So let's look at it. It's very easy, simple calculation. As usual, we consider the two frames, S and S prime, and a particle has a velocity u prime in x prime direction in the S prime frame. Question is, what is its velocity as seen by an observer in the S frame? Okay. So very simple. First, we start out by writing down explicitly how we are going to calculate u prime and u. And then we invoke Lorenz transformation. These are the transformation equations, I mean the reverse Lorenz transformation. And then we simply take a differential of this, and then we simply do dx dt. So we end up getting this result. And as you can see that, this is equivalent to simply if you put a dt over here or dt prime over here, then you end up getting this. So this is the velocity addition formula as opposed to simple ux prime plus v, as was the case of Galilean relativity. In fact, it is easy to see that in cases of v much, much less than c, this v by c square would be extremely, extremely small. Okay. So like, 12 meter per second versus 10 to the power 8 meter per second, and square of that. So you can imagine how small this number will be. So I can safely disregard this entire term, the second term, and then I will get back the original Galilean relativity result. So in the limit of v by c is much, much less than 1, you recover the Galilean relativity result. So Newtonian relativity or Galilean relativity or Newtonian mechanics was not that wrong. It only matters that under what circumstances they are effective and under what circumstances they need to be generalized. So a couple of other things on this is that if u prime and v both are less than the velocity of light, then automatically the resultant velocity is also less than the velocity of light. And if both of them are equal to the velocity of light, even then the resultant velocity cannot exceed that of the speed of light. So that is once again a confirmation of the constancy of the speed of light, and this is the highest achievable speed. Okay, so that's the sort of manifestation of this velocity addition formula. And Lorenz transformation, once again, it reconfirms that there is no such velocity greater than the velocity of light. Now, another consequence of this Lorenz transformation is that, unlike in the case of Galilean relativity, the velocities in y and z directions are also affected. You can do the calculation by yourself, and it's a simple one. See, remember that in both Lorentz transformation, in special theory of relativity, or in Galilean transformation, that is Newtonian relativity, the motion was only along x direction. I mean, the way we are sort of writing things or doing the simple one. So the y and z coordinates, they did not undergo any transformation. And as a result of that, in case of Galilean relativity, the velocities along the y and z direction did not change from frame to frame. But over here, see, once again, over here, how we are evaluating these velocities. So we are evaluating these velocities using this formula. So now you see that although y prime and y do not change, if I simply substitute this with y, then y prime and y, although they do not change, t prime and t change. So as a consequence of that, for both the y and z component of velocities, they do undergo a transformation in special theory of relativity. Okay. And once again, you can see that when v is much, much less than c, then this gamma becomes 1, and this quantity drops to 0. So that over the velocity in the y and I would request you to mute your microphone, please. Whosoever has kept their microphone on, please mute yourself. Okay, so is this part clear to you all?
So,
Yes.
so since y and z is constant, so the differentiation of it with respect to either t or t prime would be equal to 0. So how it's
No, sir. Y and Z are not who said constant? What do you mean by constant?
so with respect to that Lorentz transformation.
Huh? No, but why do you think they are constants? They do not, the Y and Z, they are not changing from frame to frame. Okay.
Yes, sir.
But what is changing is time. See, the velocity is dy dt, the rate of change of y with time in a frame.
Yes, sir.
Uy prime would be dy prime dt prime. Okay. So dt prime and dt, they are not the same. Although dy and dy prime are same, but dt and dt prime, the rate of change is not the same. So that introduces this correction. All right, you can try it by yourself. It's very easy to do. So I would urge you to try it by yourself. Otherwise, in the next day, I will start out with this. Okay. All right. So we arrive at the velocity addition relationship. The next thing that I'm going to do, as I had said, that the question must be popping up in your mind, that what is the usefulness of these things? I mean, doesn't it go beyond the formal theory? So I already demonstrated one example from high energy physics where this effect is paramount. Now I'm going to discuss something you know already, the phenomenon you know at least. It's the Doppler effect. So you know the Doppler effect, that depending on whether the source of sound wave is moving towards the observer or is receding away from the observer, the detected frequency increases as per the observer or it decreases as per the observer. Now increases, decreases means, so when we are talking about and as per observer means the detector, I mean we detect, our brain detects the frequency of the sound. Okay. So if the source of the sound, like an ambulance, is approaching you with its hooter on, it's a common experience that the the sound actually, the pitch, the intensity increases. And when it goes away, fades away, this actually dies down. So basically, the frequency that we detect is higher than the frequency at source. Or when it goes away, the frequency that we detect is lower than the frequency at source. Because all along this ambulance has been sort of emitting the same frequency. So this is what is Doppler effect, this Doppler shift. Okay. However, how do you use that in the realm of relativity, and what is it good for? See, the Doppler shift actually occurs not only for sound, it also occurs for light. And our knowledge of the motion of the distant receding galaxies comes from studies of the Doppler shift of their spectral lines. See, the galaxies, stars, everything, they actually, in there, the continuous process is going on where atoms are actually jumping from one level to another, and they are continuously emitting radiation. Okay. So these radiations can be detected in terms of, or what we call as spectral lines, okay, and can be analyzed. So each spectral line gives rise to the essentially the state of the element inside, state of the system, that from which level, energy level to which energy level it has jumped. Okay. So from these spectral lines, by studying these spectral lines and their Doppler shifts, you can actually study the motion of these galaxies. Okay. So that is what we are going to do next. But before that, a little primer on the Doppler effect. I think you already know enough of it, right? So I do not have to really tell you all about it. But here's a nice cartoon diagram. This is a source of frequency, and then the movement of the source alters the wavelength and the received frequency of sound, even though sound frequency and wave velocity are unchanged. So if the frequency at source is this, then if the source approaching, then the frequency will be this. And if the source is moving away, then this is the frequency. Okay. So when the source approaches, the frequency increases with respect to source, and when it is receding, it's actually is decreasing. So that's common knowledge. We have put them in formula, and in fact you can write it down very easily. You can see, for example, here I'm taking, I mean, this is the classical Doppler effect I'm talking about. The situation is that the source of the sound is a speaker, and the receiver of the sound is a microphone. So suppose the microphone, that is the receiver, is stationary, and the speaker is moving towards the microphone with some velocity Vs. If the frequency of the speaker is nu, that means every 1 by nu second later, it emits the sound waves. Okay. So the first wave crest, suppose it arrives at the microphone. If the microphone and the speaker at the initial stage were L distance apart, the first crest will arrive at the microphone at this time, which is simple L by V. Now, when would the second crest will arrive? We can simply think that it would be T plus L by V. Okay. But hang on. During this time of this second wave, what has happened is that this microphone, the speaker has crossed a distance of VST. Okay, so the total length that it has to, the distance between the microphone and the speaker is now L minus VST. So the correction is over here, and as a result, you can calculate the frequency of detection to be simply this, and which is, of course, less than that of the source frequency. Okay, it's the opposite thing when the speaker is stationary in the air and the microphone, that is the observer, is moving towards the speaker. So over here, once again, it's the same frequency, but the first crest now arrives at the microphone in this time because the speaker had emitted the sound wave. Now, by the time the sound wave reaches, the first sound wave reaches the microphone is not stationary. It has already crossed a distance equal to VST1. So therefore, the total length is shortened, and as a result, this is the time. Now the second crest arrives. If we clock that at time t2, once again, the length is shortened by this amount. So therefore, the frequency of detection is this. I mean, this is very simple. You have done it. So there is nothing catchy over here. Is this clear?
Yes, sir.
Yes, sir.
Okay. Now, one is tempted to apply this straight into light waves. So, I mean, one can simply say, all right, if we simply change Vs to C, done. There is absolutely no issue. But hang on. The issue is not about just replacing Vs with C. The moment we take this case of light waves, situation changes because then we are entering into the realm of special theory of relativity, and the ideas of special theory of relativity starts kicking in. So here, the way we have done this Doppler effect is we could clearly make out that out of the two frames, one with the speaker and one with the microphone, who is at rest and who is moving. Now, when we get into special theory of relativity, we do not have that liberty. Both the inertial systems are identical. So therefore, I cannot distinguish that which frame is at rest and which frame is in motion. So we can only talk about the relative motion of the inertial systems. So subjected to that, one has to derive the relativistic Doppler effect. And this is what we are going to do. And because of that, we have to also factor in the concepts of length contraction, time dilation, etc. So here we go. First, now we are talking about observer and the light source. So an observer sees that a light source is moving towards him with a speed v, according to the observer. Now the frequency of the light is nu naught when it's stationary. That is in the rest frame of the light source. The frequency is nu naught. That means according to the observer sitting on the source is flashing out lights in interval of t naught second. Now, what about the observer? Observer sees that the flashes are being emitted not in interval of t naught second, but in intervals of gamma t naught second. Because according to the observer, the light source is moving with a velocity v. So therefore, the time of the interval should be dilated. Okay. Now suppose L is the length between the source and the observer as measured by the observer, the rest length according to the observer between these two. So according to the observer, the first crest that arrives is at T1, which is simply L by C. See, according to the observer. Now second crest, according to the observer, has arrived. Okay, first of all, we have to add this interval. But according to the observer, this interval is not T naught, it is gamma T naught. On top of that, by the time it reaches, the distance is no longer L, but it has shortened because according to the observer, the light source has moved. And moved at what distance? Gamma T naught into V. Now, you simply do the math and you end up getting the frequency of detection is this, which is greater than the original source frequency. So if this observer and light source, I mean, it's in the realm of relativity, is that the observer finds that when the source is moving towards it, the frequency is higher. Exact opposite thing happens when the observer sees that a light source is moving away from it. So it's a simple calculation, and it finds that it is less than the source. So that is what is Doppler shift, and this relativistic Doppler shift, relativistic Doppler shift, we use this for navigation purposes, to study the stars and all the galactic phenomena. Okay. All right. Any question on this? Then I will talk about the last topic.
Sir, in the previous example of microphone, if by chance, let's say we take a hypothesis that the we used light instead of sound, then basically gamma was hidden, right, in the previous formula.
Gamma was hidden.
Because as the speed of sound is very less as compared to speed of light, so gamma tends to 1. So
Yes.
Gamma was basically hidden there.
Yes, yes. No. Gamma is not hidden there. I would say the other way. The gamma doesn't need to be introduced in the classical framework.
Yes, sir.
Because the concept of time dilation and length contraction does not appear in the case of things when the velocity is much less than the velocity of light.
Yeah. Yes.
Okay. So great. Now the next example I'm going to show is kind of which can sort of be little challenging to digest, but it's a very well-known example in special theory of relativity, just to give you an idea of how confusing this actually can, and how the correct understanding of the concept of measurements, the concept of time, concept of the symmetry is important in order to resolve a paradox. And there we will be using this relativistic Doppler effect result. So the example that I'm going to talk about is known as the twin paradox. So what is a twin paradox? It's basically an age-old thing. It is not a paradox, by the way. And I will show you that why it is not a paradox. I mean, unlike the farmer and the burn problem, farmer and the shade problem, where each one of them was correct from their point of view, from the point of view of the observation done in their own frame. So therefore, the bet could not be resolved. In this case, the verdict is very clear, and the verdict is really mind-blowing. So what is it? Is that we have an identical twin, a brother and a sister who were born on the same day, same date. So they are of identical age. And one of them goes in a space voyage, okay, is off to the distant galaxy with a velocity close to the speed of light. Now, and he makes a trip, comes back to Earth. When he comes back, or she comes back, she finds that her twin has become an old man. That means her twin brother has aged much more than she. So here, this cartoon actually illustrates that, see, in the clock of her spaceship, the years that have passed is from 2005 to 2047, 42 years. Whereas the clock that is on Earth, I mean, the one that is measuring the age of her identical twin, it is now 2063. So 58 years have passed. And this is not a paradox in the real sense, or in the line of this pole vaulter and the farmer's shade problem, is that both of them were giving correct statements from their point of view. And in here, if you think that there is a symmetry in the problem, you will also start to think that both of them can claim exactly same thing for the other twin. What do I mean by that? Is that simple? That, you know, one of the twins, the one who is in spaceship, goes out for a voyage, according to this twin who is on Earth, that she has moved with a velocity close to light and keeps on moving. So therefore, according to the clock that is with him, the time is dilated in her clock. So therefore, she will be younger, which is consistent with this. Compared to him, she will be younger because time is dilated. In her frame, clocks are moving slow. Okay. So that is why I actually introduced in the beginning that what do we mean by slow clocks, even in the perception of our regular usage. Okay. Now this twin, the girl, she can say the same thing, that from her frame, this is her rest frame, this guy is moving with a velocity close to the velocity of light. So the clock in her frame would run slow, and therefore he should be younger than her when the trip is over. But that's not happening. That's not what I'm saying. This cartoon actually says that to find that during what seems to be a brief trip for her, her twin has actually become an old man. But if you try to visualize from her point of view that I am in a rest frame and this guy is moving, in this frame, the clock should run slow. That means the age, the movement of time will be slower in her frame. So after coming back, I should find that he hasn't grown up as much as I have. So he should look younger. But in here, the inference is, and she finds that this twin who was on Earth has become older. So that contradicts what we had perceived to be true. Did you get my point?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Sir, could you just tell it in brief again? It's a bit confusing for me.
It's confusing. Okay, so let me have a conversation with you. This twin is moving in a spaceship. So she has a clock, and on Earth, with this guy also has a clock. So from her perspective, when the trip is over, what should she should see? That this guy is younger or older compared to her?
Younger.
Younger, because according to her, this is a moving frame, and in the moving frame, clocks are running slower. So he should be younger. Okay. Now from his frame, from his perspective, similarly, he should find this twin should be younger. Okay. Right.
Yes, sir.
Yeah. But so basically things are symmetric. And once again, if somebody wants to place a bet that who is telling the truth, we would say that nobody is, from their perspective, everyone is correct. Because it's a matter of measurement. How you are giving your description of elapsing of time. But over here the cartoon says that this space voyager comes back and finds that during what seems to be a brief trip for her, her twin has become an old man. Now, the argument that I just gave or you gave is that from her point of view, this guy was in a moving frame, so this guy should be younger, but she is finding him older. Okay, so whatever time dilation concept we have learned, this is directly in contradiction to that. Is this clear now?
Yes. Yes, sir.
Now, what is happening? What exactly is happening? Why is this thing? Because so far we thought that with time dilation concept, we can kind of, even if it's a paradox like this farmer and the shade, we will have a consistent result. We will understand that simultaneity is broken and stuff like that. But what is happening here? It completely challenges even the time dilation idea, which is already quite confusing. Okay. So let's throw some numbers. I think that would be easier to understand. So here is this thing, that they are identical twins, A and B. B rides a spaceship to travel to a planet 4 light years away. The spaceship moves with a velocity 0.8 c and comes back. Now, A calculates that it will take 10 years for B to come home. Why? And it's easy to see. A simply calculates that, okay, going back and forth, it's 8 light years. It's going with a velocity of 0.8 c. So distance divided by velocity is time. It will be 10 years, which is fine. But when B comes home, his clock says that he has been away only for 6 years. This means that the twin at home has aged faster than the traveling one. In fact, what I did not say here is that that this is the same thing that is being confirmed by A also. Okay. So the clocks, according to the clocks attached in frame of B and frame of A are saying the same thing. That is what makes it very interesting, because both the clocks should not have said the same thing as per what we have learned till now. So what is happening? So before going to do that, so could you see, I mean, can somebody say that what is the clue? What is the source of this counterintuitive thing?
Lorenz transformation.
No, Lorenz transformation is already there. So according to, if we invoke Lorenz transformation, then I just said no, that there cannot be anything absolute. That A will say that B was moving in a frame, so I have aged much faster than B. B will say the same thing. It's symmetric with respect to both of them. That is what it should have been. But over here, what I am seeing is particularly the statement once again that this one in the spaceship, what should have been, according to what we have learned so far, from this observer's point of view, this guy was moving in a frame with this velocity, and therefore he should be younger than her. But what she also finds that he is older. So even by invoking Lorenz transformation, what was expected for her to conclude, but what she observed are completely contradicted. Did you get the point?
Yes, sir.
Okay. So the point is that this should have happened, that what I just said, that her clock should have said that this guy is younger, and this guy's clock should have said, no, she is younger. It would have been, once again, symmetry with respect to each other's frame. But here, the symmetry is not there. Why so? So first, let us try to find out that what is the problem. So you see, what I just said, that this is beyond expectation, because according to him, according to her, he should be younger. According to him, she should be younger. Would have been possible if the motion was like for eternity in a straight line for 10 light years or so, for 10 years or so. Okay. See, the Lorenz transformation, the entire concept of special theory of relativity and everything is like the state of motion keeps on continuing. At no point of time, we are disturbing the state of motion. It is appropriate for inertial frames. A frame which is moving with velocity v with respect to another frame will keep on moving forever. But over here, is it happening? How does this spaceship or this Voyager come back to Earth?
The frame will have to reverse its motion
The
and
initial
change direction.
She has to reverse it. Right. Absolutely correct. She has to reverse it, reverse the motion. Now, the moment you reverse the motion, if not anything else, if I disregard the time required to reverse, because it's a small time compared to, the time scale that we are talking about, the direction of velocity has changed. So if I continue to treat this thing in one single reference frame of the spaceship, that is no longer an inertial frame, because the velocity, although hasn't changed the value, it has changed the direction, right?
Yes.
Okay. So what you tend to think now, it's not an inertial frame anymore. I have to introduce the idea of non-inertial frame. In fact, that's a small correction. That's how Einstein had done that. But hang on, we really do not have to do that. We can still do it within the framework of special theory of relativity by introducing another third inertial reference frame. So the point is that while going out, this woman is moving with a reference frame, and then she turns around. We are disregarding the turnaround phenomena, the turnaround time, because both the phenomenon and the time is so small compared to the time scales that we have considered, okay, years and so on and so forth. Therefore, we can disregard the turnaround, and her returning back to Earth is considered in another third inertial frame. So with that minor approximation, we can actually solve this entire puzzle within the framework of special theory of relativity. This entire thing is a thought experiment, by the way. There were no twins who went to space like that and found this thing. So the point is then that how are we achieving that? So we can achieve that in the following way. And the age, calculation of the age is the following way. So each one of them has a single clock that can send light signals in 1 year intervals. And each one can record the signal from the other's clock against the signal from his own clock. Okay. So the point is that things are to be measured with a single clock. You cannot have multiple clocks, number one. Second thing is that these clocks are to be bring into coincidence twice. That is, the clocks must start together and they must come back together. Okay. So in the beginning, so now imagine the situation is like that both these twins, they are actually floating around in the galaxy, in two spaceship, let's say. And then this twin, the girl, B, she fires a rocket to get going. Now don't ask me that, okay, how can you fire a rocket and, you changing the velocity from 0 to v or something, that is also acceleration in the beginning. We are actually disregarding those things. We are saying that at the very instant, instantly, there is a rocket which starts or which helps B acquire the required velocity immediately. Now, upon reaching the planet, B fires another rocket to reverse its motion. Again, things are happening instantly. And upon reaching home, B fires another rocket to come to rest. So all these three firing of the rockets, achieving velocity, reversing it, and coming to rest are happening instantly. And at that instance, we are recording. We are recording the reading on the clock. This is how we can still beat the seemingly obvious thing that this is no longer an inertial frame. Okay, so I split the thing into two different inertial frames for the person B, that is one with the spaceship, and make sure that there is no inconsistency to imagine a process which gives you immediate achievement of a large velocity. Okay, all right. Now you see. So is the process clear?
So can I repeat it once again?
Repeat what? See, how they are measuring their ages is one thing, that they are having single clocks. These clocks have to come into coincidence twice, one at the beginning of the journey and once at the end of the journey. Okay, that's how we can compare the readings with each other. And then throughout the journey, every year they decide to send a light signal to each other. Okay, and the other one is recording the signal from other's clock and then measures that, okay, now 1 year has passed. So in order to beat the seemingly obvious thing that this is a case of a non-inertial frame, what we are doing is we are breaking the reference frame of, or we are considering two different reference frame for the uh, astronaut or the space traveler, the person B, that instead of reversing the same rocket, or rather reversing the same rocket and achieving the same velocity. So how it happens? It's like that you start to fire a rocket to get going, then upon reaching, you once again fire a rocket to reverse, and then upon reaching, you again fire a rocket to instantly come to rest. All these three things, starting of the journey of B, reversing the motion, and finally coming to rest, these are all happening instantly. Okay, so that it doesn't happen.
We are firing the rocket in opposite directions.
Huh?
We are firing the rocket in opposite directions, like to come in rest.
It doesn't matter. Those processes don't matter. It's a thought experiment. Please try to understand. It's a thought experiment to drive home the concepts of relativity. Nothing else. I know that in your mind, these things which are basically, are unimportant will play a role.
Yes,
How,
sir.
in which direction rocket was fired,
Yes, sir.
and all that time, how can you achieve instantaneous velocity? Imagine we have achieved.
Okay,
Imagine we
sir.
have achieved. The point is that I wanted to see, once again, focus on the problem at hand. The problem is that according to the special theory of relativity, time dilation that we have learned, each one of them should have claimed that the other guy is younger compared to me. But the statement in the beginning says the one who has gone to space after coming back finds out that the other guy, instead of being younger, has grown older.
Okay, sir.
We are trying to understand or analyze that problem. So which direction the rocket goes is not important. Okay, yes, somebody
Sir,
asking a question?
yes, sir. Sir,
Yes.
I realize, sir, let us call, we are calling the person who is not traveling is a specific as A, right? The twin who is not traveling. Hello?
Yes. Yes.
Yes, sir. So, yes, sir. So, I understood how uh, A would think that B is traveling at speed comparable to speed of light. That A would think that B is going to be younger than me.
Yes.
But why would B think that A is going to be younger? But because Lorenz transformation is clear in this matter, right? That person who is traveling at speed comparable to speed of light will have his or her time will feel his or her time to be slowed. So person who is traveling at speed of at around 0.8 c whatever at around speed comparable to speed of light will experience time to go slower for himself,
Time
right?
to go slower for himself. No, it's the opposite. The person who is traveling, according to you, in his own frame, he is not traveling.
Hmm.
You are traveling.
Hmm. Yes, so A will so let us call A is aging at A has aged 10 years,
Wait.
but B has aged only 6 years.
Hello, excuse me.
Yes, sir.
From B's point of view, A is traveling. From A's point of view, B is traveling.
From
Is
B's
that true?
point of view, A is traveling.
Yes,
In reverse direction, right? Oh, okay. I got it. Yes, sir. It is clear now.
right. So that's what I have been saying, that both of them should have thought the other person is younger. Okay, that's
Mm-hmm.
one thing. That is one thing. Now A will still think, I mean, the way it has been placed, or that is what we are trying to solve, that according to A, B is younger. Fine. But according to B, A is older. So basically, there is only one conclusion. Both are agreeing to that conclusion. But according to what we have learned so far, that shouldn't have been the case, right? A should have found B to be younger, B should have found A to be younger as well, because it's all relative. But here, there is an absolute truth that is coming out, that both of them agreeing that B is younger, A is older,
Yes.
right? So that is what we are trying to solve. Okay, so this is the process. Now, let us see. First of all, see how things go. So as per A, that is the twin on Earth, time to cover half of the distance, that is to reach the planet. Planet is 4 light years away. If you are traveling with 0.8 c of speed, it will take 5 years. And as per B, the length of this 4 light year is contracted by the factor of gamma. So gamma you can easily calculate. So I have actually factored that in. Gamma is 5/3. So the length of 4 light years is actually 12/5 light years. So time taken to cover this distance as per B will be 3 years. So what is 5 years in A's frame, A's count, is 3 years in B's count. Okay, we agree to that? So very clearly that B is aging slowly with compared to A. Okay. All right, up to that point we are fine.
Yes, sir.
All right. Now they are going to send lights, flashes. So what is going to happen? So let us try to understand with this small diagram. What is this diagram? You can see this is called a space-time diagram. Okay.
Excuse me, sir.
Yes.
So here A is moving or B?
B.
Oh, okay, sir.
At this point of time, it's B is, I mean, the entire thing I have written down is from the perspective of A. That A finds B is moving. So he simply calculates the distance to be 4 light years, velocity is 0.8 c, it will take 5 years to reach the planet. But then he also knows, do the Lorenz transformation, that in B's frame, this length of 4 light year would be contracted. That will be 12/5 light year. So B will actually measure the 5 years time to be 3 years. All right. If B was...
Sir, let's say we consider B is moving in a spaceship. Let's say now, before starting the experiment, let's say it is moving in the east direction. B is moving in the east direction. But at this moment, we consider A moving in the west direction with 0.8 c. Now we calculate the terms. So we will say that B will take 5 years to travel the distance and A will take 3 years.
Yes.
So things will get reversed.
Yes, exactly. Up to this point,
we will never be able to come to a conclusion.
No. See, I have been telling again and again and again that had the travel been in a straight line for eternity, forever and ever and ever, both of them will say that the other guy has taken less time to travel the same distance.
Yes.
Okay. So up to this point of reaching the planet, it's all consistent. Okay.
Yeah.
Symmetric. Now the fun starts after the reversal is done. Okay, so that's what we are trying to understand using this diagram. So along the y-axis is CT, or it's a time axis, and this is the x-axis. Okay. Now the trajectory of light for A and B, or the trajectory of, let's say, in an xt diagram, just like, for a particle, you draw a trajectory by carving out points in a two-dimensional figure as xy as their coordinates, I have already told you in special theory of relativity, we start thinking in terms of an event. An event means it has a space coordinate and a time coordinate. And then you put all the space and time coordinates and then draw a curve through them. This is your trajectory in the space-time. Okay, this is the trajectory of the event. That at each point is basically when there is a space component associated with it and a time component associated with it. Okay, so now can you tell me, or rather, time is running out, so let me tell you that if I am trying to find out the trajectory, draw the trajectory of light in this two-dimensional figure, the trajectory should be a straight line with a slope 1, isn't it?
Yes, sir.
Okay, because every 1 year is equal to 1 light year in space. Every 1 year in the time is equal to 1 light year distance. So the slope will be 1. So it will make an angle 45 degree with either of the axes. Fine. Now our guy B, let's say here, I mean, I have taken it from a book, so it's Bob. All the velocities that are lower than the velocity of light, their trajectory will be fall below the trajectory of light. You can actually calculate that. So now I see both A and B's lines, and this entire trajectory is called world line. Now for the twin A, for him, the space is not changing. The space coordinate is not changing. It's 0 all the way. And for 10 years, the space is 0. Space coordinate is 0. So her entire trajectory would be in the space-time would be along this direction on this axis. Okay. And you can see there are 10 points. Each one is equal to 1 year. Okay. Agreed? Okay. Now, there is silence. People are still trying to comprehend.
Yes, sir.
So for him, it's always x equal to 0. Only time changes. And in this particular problem, he has counted time all the way up to 10 years. So there are 10 equally spaced points. Now for the other guy, it's a trajectory because it's space and time both are changing. Now, when we draw that thing, we have to be a bit careful because, I mean, see, this is the time axis for that guy. This is basically the time axis for that guy. Okay. So this time axis is at an angle with this. That angle you can find out from the Lorenz transformation. Now on this time axis, you can see, as I had calculated, that it will take 3 years to reach the planet. So you see, there is exactly 1, 2, 3 points. Okay. And the third point, the 3 years on his time axis is exactly equal to 5 years on the time axis of A. So A is 5 years, B is 3 years. What we had calculated is consistent. Okay. So on this time axis, there are equally spaced points 1, 2, and 3. So to reach this planet, it will take 3 years. Right? Now it's reversed. Okay. Now it reverses and goes and meets here. Because this is the turnaround point. Now it starts to move towards the other twin. So therefore, this direction, this world line is basically reversed. All right. Now what happens, you see? This A, in 10 years, every year he is supposed to send one signal. And he has indeed sent one signal. Now what is happening is this. So how do I represent the signal of light? Is that from here you draw for lines, straight lines which are making angle 45 degree with this axis. So you draw the lines. The first line you see is meeting this axis at this point, at this turn around point. That is, the first ray of light, flash of light, is reaching this guy after a time of 3 years in his frame. Okay. Then there is a turnaround. So all the other 9 signals have reached this guy B during her return journey. So we had thought that if he has sent 10 signals, 5 of them will reach in the onward journey and 5 of them in the return journey. But that hasn't happened. And that confirms the asymmetry in the problem, that the first signal has reached right after 3 years at the turnaround point, and rest 9 signals have reached during the return journey. Now, the signals that are being sent from B, they had agreed to send signals. So here is the first signal. Here is the second signal. So during the onward journey, there are only 2 signals. And every 3 years, they are reaching A every 3 years in his clock. And then another 3 are in the last 1 year. So first 3 signals have reached every signal, 1 signal after every 3 years. So within 9 years, he has got 3 signals and another 3 signals in the last 1 year in his clock. So he records altogether 6 signals. And then he concludes that yes, indeed, the other guy is younger, and so is she. I mean, the space voyager, because she had sent 6 signals anyway. You can see that this guy had sent 10 signals, but this guy could send only 6 signals. It's not that she didn't want to, but her time is dilated. So what was 1 year in this frame, it's longer in that frame. The concept of 1 year is lengthier in that frame. And then she is sending signals. So there are only 6 signals she could send. So she is sending signals from her clock and saying, okay, I am 6 years old. And she is receiving 6 signals only. So he also concludes, yes, he is 6 years old, but I am 10 years old. Because this guy has received 10 signals from him. So she can indeed say that A is 10 years old, because during the entire journey, I have received 10 signals. Okay. And A is also saying, yes, I have sent 10 signals. But then from B, A has received 6 signals only. And B is also confirming that, yes, in this 10 year, I mean, I have sent 6 signals because my age is 6 years. Okay. Now, what is going on really? From where am I getting this information? And what is the veracity of the fact that I have been drawing these pictures? So one thing is confirmed, that 5 years is equivalent to 3 years over here. But then the other things, particularly this length, that where these lights have been hitting. So let me show you a very small example. You can work out the rest to cross check it. Let me go right over here. So here in the supplement, you can see that according to B, 4 light year is contracted to 12 by 5. So he can cover this distance in a time of 3 years, according to his clock. Now, in 1 year, how much distance B has covered? In 1 year, 1 year means 1 light year distance. And, you know, in 1 year, B can cover a distance of, in 3 years, if it covers 12 by 5, in 1 year, it can cover distance of 4 by 5 light years. Okay. Now, after covering this distance, he sends a pulse, his first pulse. What is the time span as per A's clock when the pulse reaches A? Okay, because that is when the A, according to his clock, will get the signal. Now, according to B, the light should reach A after 4 by 5 years. Because when B has sent the pulse, he has covered already a distance of 4 by 5 light years. I am sending the pulse. The light will take 4 by 5 years to travel back to A. But in A's clock, by that time, due to the time dilation, the time elapsed is 4 by 3 years. So 1 year in B's clock is actually 5 by 3 years in A's clock. So you can see that's how 3 years in B's clock, I mean, this factor, I mean, every year in A's clock and B's clock correspond to this thing. So that's why, I mean, if we go back, so that's why the first pulse that is being received from B will be clocked 3 years in A's clock. So you see, again, if we go back, the first pulse that A receives from B is after 3 years in his own clock. So this little calculation can make you understand this thing. Now, can we try to explain this, that why this asymmetry in reaching of the pulses? We can actually explain it using the relativistic Doppler effect. That when B makes an outward journey, the clocks are moving away from each other. So signals reaching each other at a slower rate. And we can actually find out the factor by which it is slow. It's 1/3. So that means every 3 years, one signal from other's clock is received by each one of them, which means that B receives one signal from A, B receives one signal from A after 3 years in his clock, and same goes for A. Okay. Now, this signal, when it reaches from A, by that time B is about to start its return journey. Okay. Now, when it's about to start its return journey, see, from B, it had already sent signals before it's making a turnaround. It's another matter that the signals are reaching really late to A. By the time A is aged, A is aging fast. So that's a different thing. But B has sent 3 signals before the turnaround point. Okay.
Fine.
Now, when B is making a journey, clocks are moving away, moving towards each other, not away, moving towards each other. So then the frequency of the receiver is larger as compared to the rest frequency, which means the signals are reaching at a faster rate. And the signals are faster by a factor of 3. That means in 1 year, 3 signals from others' clock is received by each one of them. So that is why B is receiving 9 signals from A, because B is making a 3-year journey according to his clock. So in each year, he is receiving 3 signals, because according to him, he knows that he is actually heading towards A, right? And in case of A, since 9 years have passed, means this last signals has been received from B. Now in last 1 year, A receives 3 signals from B. So that makes the total signal that A receives is 6, while the total signal that B receives is 10 altogether. But the fact is that both of them are agreeing that the age of A is 10 years, while the age of B is 6 years. Okay. So it's quite an involved thing, and it's quite a bit of a mind-blowing example of this twin paradox. But this is a thought experiment, as I said, and it essentially illustrates that a symmetrical condition, we have explored the symmetrical condition, and we sort of kind of understood the relativity of sorts of time, ages. But in this case, when the situation is asymmetrical, then you have to be very careful. Then there is only one truth, the absolute truth, so to say. There is not because the situation as perceived by the one who is stationary, quote unquote stationary, and the one who is making a round trip, the situation is asymmetrical from their frames. So therefore, the twin paradox is not really a paradox. It appears to be a paradox, but it's not a paradox. The moment you discover that it's an asymmetrical situation and you cannot really fix one inertial frame to the observer or the traveler, you have to make do with 2 different frames, one in the direction, one which is moving towards the other observer, and one which is moving away from the other observer. Okay, so I'm sure that your brain must be throbbing with lots of questions, but we have spent 1.5 hours on this. And before we close our course on special theory of relativity, I will surely address these issues maybe in the next lecture. So read it up, note down all your questions, and we will have a discussion on this after the next.